Assalamu alaikum to you all. Welcome to the lecture of chemistry. We are studying the chapter transition and inner transition elements. And in our previous lectures, we have completed the discussion about the transition element, that is the D block element. Today we are going to learn about inner transition elements. Let's see what is mean by inner transition elements. Inner transition elements are the elements that belongs to F block in the periodic table. And what are F block elements? The elements in which the last electron enters into n-2 f orbital are known as F block elements. Now here the point to be noticed mainly here is that the last or the differentiating electrons does not enter into the outermost principal shell, but it enters into n-2, that is pre-penultimate f orbital. Okay, now what is the meaning of penultimate or pre-penultimate? There is one outermost shell which is represented by n, and the shell which is inner to that outermost shell would be called as penultimate shell, and the shell which is inner to the penultimate shell would be called as pre-penultimate shell. For example, suppose your outermost principal shell is sixth, so your pre-penultimate f orbital would be what? It would be 6 minus 2, that is 4f orbital. Okay, now these f block elements are called as inner transition elements. Why do we call them as inner transition elements? Because these f block elements lies within the series of transition series, that is d block elements. Since f orbitals are inside the d orbital, and this series of f block element also lies within the transition series, that's why we call them as inner transition series. Now we'll get understand it better when we'll look at the periodic table. Okay, now here is your periodic table. We know that in periodic table the atoms are arranged according to the electronic configuration of the elements. Okay, on the basis of this we have divided the elements into four blocks. On the left hand side we have S block elements, on right we have P block, in the middle we have D block, and at the bottom we have F block. Whenever we say the periodic table, we know that the periodic table is made up of 7 periods and 18 groups. Now 7 periods and 18 groups are over if you leave the last two or the bottom two series. If you don't look at the bottom two series, then too your periodic table will contain 7 period and 18 groups. Then from where these F block elements are coming from? You can look in your 6th period and 3rd group and 7th period and 3rd group. There are two elements, lanthanum and actinium, which are placed in D block elements because their last electron or the valence electron in them enters into D subshell. Okay, now here what happens, after lanthanum, the 14 elements which should come after lanthanum progressively according to atomic number are missing from the periodic table. Now those 14 elements are placed at the bottom and they constitute the first series of F block element. In the same way, when you look at the 7th period into the 3rd group, there is an element actinium 89. Now you will find that after actinium we don't have the element with atomic number 90, but there are some elements from atomic number 90 to atomic number 103 are missing and the next element in the periodic table comes with atomic number 104. So these 14 elements are again placed at the bottom of your periodic table. So you should remember that your F block is interrupting into the 6th and 7th period of the periodic table and the third group of the periodic table. Since in these 14 elements, altogether 28 elements, the differentiating electrons are entering into the F orbital. That is why they are called as what? F block elements, and they are placed, or they have been given into a new position into the periodic table. This is just to maintain the symmetry of the periodic table. Now the 14 plus 14, 28 elements which are forming the F block are divided into two series. The first series of 14 element is known as 4F series, because in these 14 elements the last electrons are going into 4F orbital. In the same way, the next last F block series is known as 5F series. Here, the last electrons are entering into the pre-penultimate 5F orbitals. Okay. Now, lanthanum and actinium are also written here just to show that these lanthanum and actinium are the prototype of the elements that are present in the series. The first 4F series is known as lanthanoid series because the 14 elements from cerium to lutetium resembles lanthanum in their chemical and physical behavior. In the same way, the next series, that is 5F series, is known as actinoids. All the elements of 14 elements are known as actinoids because all the 14 elements from thorium to lawrencium resembles actinides in its resembles actinium in its chemical and physical properties. Okay, so this F block series can be divided as lanthanoid series and actinoid series. Whenever we say lanthanoid, it means we are referring to all the 14 elements that are present in the 4F series, and whenever we say actinoids, we are referring to all the 14 elements that are present in 5F series. So there are 28 F block elements. Lanthanum and actinium itself are not F block, they are positioned in the D block because in these two elements the last electron is not going into the F block but into the D block. So F block remains empty in them. That's why they are not given. They are given position in the D block. I hope you all have understood it. Now let's see the simple characteristics of these lanthanoid and actinoids. What are lanthanoids? The elements of the lanthanoid series are characterized by the preferential filling of 4F orbital. It means in these elements, all these 14 elements, you will find that the valence electron or the last electrons, when you write the electronic configuration, you will take the help of what? An Aufbau principle, that energy diagram for filling of the orbital, and you will find that your last electrons are going into 4F orbital. It includes 14 elements from cerium 58 to lutetium 71. Altogether, these lanthanoids can be represented by a general symbol capital L small n, that is Ln. The name of the series is after the preceding element lanthanum, with which these elements closely resemble. we know that all the lanthanoids exhibit similar physical and chemical properties as that of lanthanum. That is why they have given the name as lanthanoids. In the same way, we can also describe actinoids, that these are the elements which are characterized by the preferential filling of 5F orbitals. It includes elements from thorium 90 to lawrencium 103. In this uh, picture, it is written as Kr. It is wrongly written as Kr. It is Lr. Okay, Lr 103. That is lawrencium 103. The name of the series is again after the element actinium, with which these elements closely resemble in their physical and chemical behavior. Now, there are some important properties which are mentioned in the text. Lanthanides have lower heat of atomization than transition metal. Now we are comparing the inner transition metal with transition metal. We found that lanthanoids have lower heat of atomization. It means they are easy to break as compared to the D block element. What is this enthalpy of atomization? The energy required to break up the metal lattice is called as heat of atomization or enthalpy of atomization. Okay, so lanthanoids have lower enthalpy of atomization as compared to D block elements. The ionic radii of lanthanoid decreases from 117 picometer of lanthanum to 100 picometer of lutetium. So when you look into the series of lanthanoid, from lanthanum to lutetium, the atomic size or ionic radii decreases from 117 picometer to 100 picometer. So the decrease between the 15 element is only of 17 picometer. So this decrease is very gradual, very small. Now, why this is happening? This is because the 5F orbitals do not shield the outer 5s and 5p electrons effectively. The electrons which are the orbitals, look, we have the 4f last electrons entering into the 4f subshell. Okay, so this 4f subshell have 5 and 6 principal quantum number or principal shell above it. Okay, but the 5f and the 5s and 5p, they do what? They will effectively shield it from what? The electrons, from the effect of any ion or the ligand or attacking group. So these 4f or electrons which are present in the lanthanoids are nicely shielded by the this thing, attack of any ion or attack of any chemical species, leading to what? Increase in effective nuclear charge. As they are quite inside, they experience what? Good effective nuclear charge, good attraction by the nucleus, due to which the ionic size also decreases. Okay, when the effective nuclear charge increases, the ionic size will always decrease, and when there is less shielding effect, the effect of effective nuclear charge would be very strong. Now all the lanthanoids will form hydroxides of the general formula LnOH thrice. Like alkaline earth metal, these can form what? Hydroxide, that is base. Now these lanthanum hydroxides are ionic and basic in nature. It means they may dissociate into water and they are basic in nature. As the size decreases, look here, exercise is written, it is size. Since the size decreases from lanthanum to lutetium, the basicity of hydroxide also decreases. It means from lanthanum to lutetium, the basic character of the lanthanum hydroxide will go on decreasing due to decrease in size. Now these lanthanoids are able to react with nitrogen and halogen to give nitrides and halides of the formulae LNN. So one lanthanide, any lanthanide would be there with one nitrogen atom, and LNX3, that is for one lanthanide there would be three halogen atoms. Okay. Lanthanoids can also react with carbon at a high temperature to form carbide with the general molecular formula LnC2. Now remember here that if in place of this lanthanum Ln, any of the lanthanoid elements symbol is mentioned, then too the formula which is given as the formula of the product remains same. For example, suppose in place of lanthanum, they would have given cerium. So the cerium on reaction with nitrogen will form CEN. Cerium on reaction with halogen will form, take any halogen, chlorine, bromine. The cerium with reaction with chlorine will form CeCl3. The cerium with reaction with a carbon will form CeCe2. So with any of these lanthanoids out of all the 14 lanthanoids, the reaction could be asked, but the formula of the product will remain same like this. Now there are some properties of lanthanoids. These lanthanoids are soft metal with white silvery color. Okay. Their density is approximately 7 gram per cm cube and its brightness will reduce on exposure to air. They are good conductor of heat and electricity. All the lanthanoids are non-radioactive except promethium. Promethium is also made in laboratory. It does not occur naturally. The atomic and ionic radii decreases from lanthanum to lutetium. Why it decreases? Because the effective nuclear charge increases significantly. And this decrease in the size of atomic or ionic radii is known as lanthanoid contraction. Now binding to water is common, that is such that water is often found as the product when isolated from aqueous solution. It means lanthanum has the very good affinity, all these lanthanoids have the good affinity with water, and they exist in the hydrated form. So when you isolate a lanthanoid, any lanthanoid, you will find a water along with it. Okay, that is why it is written here as that binding to water is common, because it absorbs water and its binding fit with water is very good. Now the coordination number is usually very high. The coordination number of the lanthanoid is high at the level of 8, 9 or up to 12 also. Okay. Next is the lanthanoids are strongly paramagnetic. They are paramagnetic. Why? Because they contain unpaired electron in their f orbital. Okay. Because of the presence of unpaired electron, they become paramagnetic. The other heavier lanthanoids, terbium, dysprosium, holmium, erbium, thulium and ytterbium, become ferromagnetic at very low temperature. Okay, it means that all these are paramagnetic, and many of these have the ability to become ferromagnetic at low temperature. Magnetic and optical properties are largely independent of environment. That is, what are the ligands or the ions or the atoms that are attached to lanthanides will not have a good effect on its magnetic and optical behavior.